hierarchical deep reinforcement learning algorithm that enables robots to learn both basic and compound skills at the same time. The algorithm uses a two-level hierarchy. The first level learns basic skills, each with its own actor and a shared critic, while the second level learns compound skills by reusing the basic skills overseen by a metacritic. The proposed model is evaluated on a Pioneer 380 robot in three different navigation scenarios using simulations built in Gazebo 2 with a robot operating system Indigo environment. Results show that the algorithm can successfully learn high performance basic and compound skills through a unified learning process. The compound skills learned by this hierarchical approach outperform those learned by a discrete action space deep reinforcement learning algorithm. The motivation of this paper is the continuous action space challenges. Robotic control often involves continuous action spaces which are more complex than the discrete ones. This complexity makes it hard to design effective reinforcement learning algorithms. Skill learning for compound tasks. Robots need to acquire both basic and compound skills to solve complex tasks, but existing methods struggle to achieve this simultaneously within the same learning process. Limitations of existing methods. Traditional reinforcement learning methods, including deep reinforcement learning approaches, perform well for basic locomotion but fail to efficiently handle compound tasks. Hierarchical learning opportunity. Hierarchical structures in reinforcement learning can potentially improve skill acquisition by separating basic and compound skill learning processes while enabling reuse of learned skills. Unified learning process. The authors aim to develop an algorithm that integrates both levels of skill learning into a single time-efficient process, overcoming the limitations of multi-threaded or time-scale separated approaches. The methodology. Here the algorithm uses two-level hierarchy for skill learning. One is handled by individual actor networks, one per basic skill, overseen by a shared basic critic that evaluates all basic skills. And the second is managed by a metacritic that combines basic skills into complex tasks, reuses pre-learned basic skills to reduce computational complexity. And basic skills learning. Each basic skills, example movement primitives, has a dedicated actor network but shares a critic. ML multi-layer perceptron convolutional layers reduce parameter count while enhancing feature recombination. Shared critic enables coordinated learning across skills by evaluating their combined performance. Compound skills learning. Metacritic learns to sequence basic skills for compound tasks. Example, navigation with obstacle avoidance utilizes a deterministic policy gradient approach inspired by DDPG, deep deterministic policy gradient. Compound policies outperform discrete action RL methods in simulations. And the neural network structure is actor networks input sensor data, example LiDAR, and first-person camera images. Output are continuous control actions, the motor speeds. Critic networks and convolutional layers process visual inputs. Fully connected layers handle sensor data and action inputs. Target networks stabilize training via delayed updates. Simulation setup is the environment Gazebo 2 with ROS Indigo, robot Pioneer 380 equipped with range sensors and a front-facing camera. The experimental results is as follows. As you can see, the graphs show the performance of the actor for going forward, for turning right, for going backward, and as you can see, it completes the task accurately. You can see the performance of each actor in 3 scenarios. The pictures at the bottom right of each curve are samples of moving trajectories of the actor. The yellow triangles indicate the initial orientation. The experimental results. The hierarchical deep deterministic policy gradient algorithm successfully learns both high performance basic skills and compound skills simultaneously within the same learning process. The compound skills learned by HDDPG outperform those learned by a discrete action space deep reinforcement learning algorithm in the three simulated navigation scenarios. This suggests that the hierarchical approach is more effective for complex tasks requiring continuous control. The algorithm effectively uses observations from both sensor data and first-person view camera images to learn the necessary skills. The convolutional layers help reduce the number of parameters needed for learning multiple tasks. And this is a comparison table for the previous algorithms. The overall performance is improved in the proposed algorithm. It shows improved performance over discrete action space DRL in complex continuous control tasks, provides more reactive control than some other hierarchical RL algorithms by learning in the same time scale. And this algorithm addresses the limitations of standard deep RL algorithms in efficiently solving compound tasks that require learning both basic and higher level skills. The conclusion is that the paper introduces a hierarchical deep reinforcement learning algorithm that can learn both basic skills and compound skills simultaneously. The algorithm addresses robotic control in continuous action spaces, which is a challenging area. And it utilizes a two-level hierarchy, one for learning basic skills with individual actors and a shared critic, and another for learning compound skills with a metacritic reusing the basic skills. The proposed algorithm can learn both high-performance basic skills and compound skills through the same learning process. The learned compound skills outperform those learned by a discrete action space deep reinforcement learning algorithm. The main contribution is a hierarchical deep reinforcement learning algorithm that can learn multiple basic skills at the same time, learn compound skills by reusing basic skills, and handle both kinds of skill learning within the same process and time scale. Thank you.